Hi everyone, welcome back to Data Cadence. My name is Rahul and I work as a senior applied research scientist. And in today's video, we are tackling a crucial topic for any aspiring data scientist or machine learning engineer, that is understanding the time complexities of fundamental machine learning algorithms. So why you should care about the time complexities? Well, it's more than just a number. Knowing about the time complexity of an algorithm tells you a lot about its efficiency and how it scales as your data grows. And it also helps you choose the right algorithm for your problem, ensuring you balance between accuracy and the computational feasibility and the runtime and the training time that it would take for your particular algorithm. And also, when you are in an interview, demonstrating a solid grasp of these complexities can set you apart. It shows that you not only know how to apply these algorithms, but also understand their underlying mechanics. And you're not just running black box models, but you're making informed decisions based on how these algorithms perform with the increasing data volumes. So let's break it down. And again, I'll just go over each of these algorithms, the most fundamental algorithms, but you don't need to mug up these time complexities. We'll talk about the intuition behind each one of these and how each of these time complexities are coming up, because each algorithm's complexity comes from the core operations that they performed, whether it's distance based calculations, matrix operations, tree traversals, or optimization routines. So without further ado, let's begin. The first algorithm in our list is going to be KNN. So the training time complexity for KNN is O of 1, because as we know that KNN doesn't involve any training phase. It just stores the data, and we had discussed this in one of the earlier videos. Because of the same reason, it's also called as a lazy learner. The runtime complexity for KNN is big O of n times d. So for each prediction, KNN needs to compute the distance to all the endpoints in the dataset with d dimensions. And like we mentioned, n refers to the number of data points or observations, and d refers to the number of dimensions or the features. So it's pretty straightforward. When it comes to logistic regression, so the training time complexity is big O of n times d times k. N and d are similar, number of rows and number of features respectively. K is the number of iterations. And the training of logistic regression involves iterative optimizations, so something like gradient descent. So, and that is the reason that you see that the time complexity is big O of n times d times k. The runtime complexity for logistic regression is big O of d, and the prediction involves simply a dot product between the weight vectors and the input features. And you see that it has one of the least runtime complexities when it comes to a lot of algorithms, and that is the reason that you prefer logistic regression for a lot of the low latency use cases that you might be trying to solve, where you have to make the prediction in almost real time or near real time when you are having any use case. So definitely logistic regression does shine on that particular one. The third one is decision tree. So here the training time complexity is big O of n log n times d. And why? Because building a tree involves splitting the data at each of the nodes, which requires sorting the data for each of the features. So if you have d features and you want to sort the data for each one of them, so the time complexity of sorting is O of n log n in a general case. And d, as I mentioned, you need to do this for all the features, and therefore the training time complexity is big O of n log n times d. The runtime complexity is just O of log n, because the prediction involves traversing the tree from root to the leaf, and in a generic scenario it is usually the height of the tree when you want to traverse from the root to the leaf. And again, in a generic scenario the height is generally given by log n, although it can be extended to O of n if you have a skewed tree, but let's not go there. In a generic case you can say that the runtime complexity is O of log n, because in decision tree you don't usually end up with a skewed trees. The fourth one is support vector machines or SVMs. So for SVMs, the training time complexity can vary significantly. It could be either O of n squared times d, and it could be as high as O of n cubed times d. Why? Because the complexity depends on the optimization problem for SVM, which in this case is quadratic programming, and it scales poorly with the number of samples. And when is it each one of these? So you have big O of n squared d in more efficient implementations of SVM using methods like SMO, that is sequential minimal optimization. And you have big O of n cube times d for less efficient implementations, where the solver that you are having directly tries to handle the n cross n matrix for the quadratic optimization. So it could vary, but in general you can say that the time complexity varies from big O of n squared d to big O of n cube d. And the runtime complexity for SVM is also straightforward. It's big O of n times d, because the prediction involves computing the dot product with the support vectors, and that's pretty straightforward. When it comes to random forest, so random forest being an extension of decision trees, the only additional thing that would add is the number of trees, and therefore the training time complexity is given as big O of m times d times n log n, where m is the number of trees that you have in your random forest, and each tree has a similar complexity similar to a decision tree, and that's why you have this n log n times d which stays constant. By similar logic, the runtime complexity for random forest is given as m times log n, because you have m trees and traversing each one of them would take in log n time, and the prediction involves averaging the results of m trees, and therefore you have a runtime complexity of big O of m times log n. GBDTs, or gradient boosted decision trees, or XGBoost, whatever you may call it, they also have the similar time complexity. So it's big O of m times n times d times log n, and this is because each tree is built sequentially, so the complexity is similar to random forest. That is the only difference, that in GBDTs you build the tree sequentially, but from a time complexity standpoint it stays the same for both random forest as well as your gradient boosted decision trees. When it comes to runtime complexity, so the runtime complexity is again similar to a random forest, but the trees here are typically shallower, so you can say, but again we take it for the worst case when we consider big O, so we can say that it's big O of m times log n. Let's talk about naive Bayes. So naive Bayes, the training time complexity is big O of n times d, because training involves calculating the conditional probabilities for each of the features, and therefore it's big O of n times d. For a runtime complexity, it's only big O of d, because prediction is simply multiplying the probabilities that you have obtained for each of the features, and that is another reason that naive Bayes is also, it could be a good choice for use cases where you have to have a low latency at the runtime or at the inference time. Let's talk about the last one, that is artificial neural networks. So for artificial neural networks, the training time complexity is given as big O of n times d times l times k, where l is the number of layers in your artificial neural net and k is the number of iterations or epochs for which you want to train your particular neural network. So L is the number of layers, K is the number of iterations, and backpropagation scales with the number of samples, features, layers and iterations, and therefore you have n times d times L times K. And for the runtime complexity, the prediction involves a simple forward propagation through the network, and this will essentially depend on the number of layers and the input size, and therefore the runtime complexity would be big O of d times L for an artificial neural network. So this was another video in which we tried to understand what is the runtime complexity behind each of the algorithms and how that particular thing is derived, what is the logic behind it, and hopefully this gives you a clear understanding of which machine learning algorithms make sense for what kind of problem statement that you might be trying to solve. And also, like I mentioned, it's a very good and a healthy signal to the interviewer or the potential employer that you understand the fundamentals of these algorithms and how they would scale as your data grows more and more. So hopefully this video gave you some insights. If it did, please consider pressing the like button. And if you are new to this channel, subscribe for more such content. So I will see you in the next video then. Until then, take care, stay safe and keep learning.